So let's start, but maybe let's check that the sound is recorded or whatever. Broadcast. Shall I say something? I'm saying something. Yes, I'm saying something. No, I am saying. Fine. Great. Thanks. Thank you. So we continue our preparation for the proof of existence of Hilbert scheme, and the whole week, this whole week will be just preparation, and then next week hopefully we will prove this theory. So we'll start with some basics of flat morphisms. And we proved some lemma last time. It was lemma 1 about base change up to a big twist. Okay, it was proved, and today we'll have some more lemmas. Lemma 2 says that given a coherent sheaf on a projective space over a base scheme, if we know that there is some big enough positive integer such that the direct image we always denoted by pi to the base scheme. Is locally free over the base for any r bigger than n, then f is flat over S. So it's a criterion of flatness. Okay, so if after big enough twist the direct image becomes locally free, then your initial sheaf was flat over S. Pardon me? Yeah, yes, over the base, yes. But we assume that it's not just flat, but locally free. And then we will derive that the original sheaf F is flat over S.
But F is a sheaf over
yes.
the projective space?
Yes, but this projective space lives over S, so your sheaf F also lives over S. It makes sense to claim that it's flat. Yeah. So the proof is very short. So we consider again some graded module. Namely, this direct sum of locally free guys. Okay, and then we know that this one is flat over OS. Okay, and so it means that it's any localization of this module will also be flat over OS. And we consider the following localizations. So we say that our projective space is the relative projective spectrum of OS of x0 and so on, xn. Okay, just as we did over some ground field, then it's a relative version of this construction. And I say that the localization m with respect to xi is also OS flat. And now this module where you allow xi inverted is also graded. I mean, x has degree 1. But since xi is inverted, it is graded not positively, but by all integers. Let's take component of degree 0, m0 xi of degree 0. It's direct summoned. Yes, it's a graded module. It's just 0 direct summoned. So it's also flat. As a direct summoned of a flat module, it is flat. On the other hand, this module, degree 0 part, but by definition is the global sections of the open chart of this project space with coefficients in our sheaf. So UI is a standard affine chart of U and S. Yes?
You mean here localization of global sections over this
Well, I mean just exactly what is written.
M is
That-
a sheaf, M0.
Yes.
No.
No.
The right hand side is a module.
Well, it's OS module, and this OS module. And these two OS modules are equal. Everything here lives over the base S.
Gamma sections over U is a module, not a sheaf. And the left hand side.
Okay. But I think you understand what is going on, and I can write pi restricted to UI of f, maybe again restricted to UI, but I think it was clearer in the previous notation, no? Okay. So our projective space is the union from I goes to 0 to n of u i's, and hence f is flat. Right? All these guys are flat, and u i's cover the whole project space, so f is flat. And we are done. Okay. Now the next lemma 3, so-called generic flatness. Says the following. Let B be a finitely generated A algebra without zero divisors. In particular, A is also integral, that doesn't have zero divisors. And M a finitely generated B module. Okay. Then there exists a non-zero function, well, element of our ground ring A, such that if we localize with respect to this element, then the localized module is free over the localized ring, and in particular flat. So every module is generically free and hence generically flat. Okay.
Is A necessarily an incoherent?
Yes, yes, because B has no zero divisors and it's an algebra, so A is in little domain. Yes. Well, since we need to prove the generic flatness, let's go to the generic point. That is, K is the fraction field of A. A has no zero divisors. And Mk is the corresponding vector space over A. But this vector space is infinite dimensional in general. Yeah, M is finite over B, but not necessarily finite over A. Yeah, B is finitely generated. Like A could be just a field, and already to begin with, so that would do nothing at all. But B can be a polynomial algebra, and this will be just this is the same infinite dimensional polynomial algebra. Okay, so. This is a finite BK module. So BK is also K tensor over A with B. And we said N is the dimension of the support of this module over this, well, how to say, well, support in the spectrum of BK. Dimension of this support. And we will argue by induction in N. And we will start with empty. Support, so N equals -1. And so the support is empty. So Mk is 0. Okay. And it means that any vector in M is annihilated by an appropriate element of A. Okay. Now M was finitely generated, so we can choose finitely many generators. V1 and so on, V capital N generators of M and the corresponding elements A1, so on, A capital N in A, and then take their product, and this finite, well, it will be a finite product, so it will be some element of A, which annihilates all the generators of M and hence annihilates the whole M. Okay, so set f is a1 times so on times an, and then fm is 0, and hence the localization with respect to m is also 0, with respect to f is also 0, and well, it's a free module, so we proved our theorem in this case. Yes. Oh yes. Oh yes. So generically the model is just 0, and in particular locally free. Now we can start our induction process. Now at least 0, and since m is finite over B, it has a filtration. And why did you stop taking notes, or did you never tried? I'm sorry, just an idle curiosity. Huh?
I write the statements.
Not the proof.
Yeah.
Okay. But unfortunately, today we'll have not many statements, but quite a few proofs. Okay, so has a filtration. Like this, so that all the successive quotients are like simple bimodules, so to say. Mi over mi minus 1 is isomorphic to B over pi, some prime ideal.
What do you mean by A are corresponding elements of V class?
Well, I mean that any element is annihilated by some element of any vector in M is annihilated by some element of A. In particular, any generating vector is annihilated by some appropriate element of A. And then I take product of all those, and the product of all those guides annihilates every generator, so every element of M at all. Okay? Yeah.
Was the base of induction?
Yes. That if our module is small enough, then it's generically 0. And now it's not very small. So when we go to the generic point of A, it has it does have some support, at least 0-dimensional. So it lives somehow over all the spectrum of A. So there is this spectrum of A. There is some bigger, oops, sorry. Spectrum of B, and inside here there is some support of M. Okay, but we know that at least generically it does project non-trivially to onto the spectrum of A. Okay. Otherwise, the model generically is 0. So we filtered, we have the associated graded, and if we can prove our theorem for each step, then certainly we can prove it for the whole module. So it suffices to prove our lemma for each mi over mi minus 1, that is isomorphic to b over some prime ideal. But then we can just replace b by this quotient algebra. So we can assume that now M is just B. It's just a free B module of rank 1. Okay. So we know that n, and the dimension of support generically is at least 0. It implies that the localization is not 0, and hence A is embedded into B. Under this projection, A is a subring of B. Yeah, because well, A has none of them has 0 divisors, by assumption. Okay, and now by the Noether lemma, well, we can pick elements B1 and so on, B n in B, such that the localization Bk is finite over the polynomial ring like this, and in particular B1 and so on, Bn are all algebraically independent. Yeah, if you still remember what is Noether lemma, then it's one of the formulations. Okay, so let G in A be the common denominator of all the equations with integral coefficients integral coefficient, I mean in this polynomial ring of all the generators of Bk over this polynomial ring. Okay, so our assumption is that our module is module generator. It happens to be a ring also, but just in this sense. Okay, so there are equations for the generators. They are all integral, and let's take all these equations, all their denominators, and take the common denominator. Great. So we're almost done. And now we see that if we localize our B with respect to this common denominator over the localization of our polynomial ring. Okay. So I mean the same was true just over the whole fraction field, but in reality, since everything is finite, only finitely many denominators are involved, and it's true over some finite localization. We don't need to invert everything at all. Okay, so let M be the generic rank of this module. And it means that we have the following extension. We have this localization of the polynomial ring, M copies, then it's embedded into the localization of our module, and well, generically it's an isomorphism, but somewhere on the boundary we have some quotient module, and we see that this T is a finite module over the polynomial ring. And again, generically, this embedding is an isomorphism. So this quotient T is a torsion module. And in particular, it has smaller dimensional support, and we know what we want by induction assumption. And for this free module, well, it's already free, so nothing to prove. And so we are done by induction. So it's a free finite. So T is a finite module of torsion, and its support is smaller dimensional. Decay is less than n, and well, by the induction assumption, there is some well, f prime such that the localization Tf is free, Tf prime is free over a f prime, and well, and set f is f prime times g, and we are done. I mean, for this module, it's clearly free. This is free by induction assumption. And we take the common localization. Fine. So this is proved. And we will need the following corollary, the generic flatness. Yes? Say again, what about the Nakayama lemma?
To prove in the case n is minus 1, it looks like Nakayama lemma in commutative algebra.
No, I don't think we used Nakayama lemma here. We'll use it in 5 minutes, but so far I don't think we used it.
Можете, пожалуйста, еще раз конец рассуждения повторить?
Yes.
Начиная с той же последовательности.
Yes. So, what shall I repeat? That well, generically, well, this has well, if we localize to the whole fraction field, this will be just a free module with M generators. Okay, but well, we don't actually need to go to the whole fraction field. Just some particular element has to be inverted, and well, we have such a morphism, and generically it's an isomorphism, but it may have some quotient on the boundary. I mean, everything here is embedded into the total localization, because all our algebras are integral. A and B are integral, no zero divisors, and so everything embeds into well, BK, and this is also BK polynomial ring like this. Okay, and we know that this is an embedding, and hence this since everything is embedded in the upper row, this is also an embedding. But this embedding is an isomorphism generically. So the quotient.
What do you mean by this embedding is generically
Well, if you localize to K, if you replace A by K by its fraction field, then it's an isomorphism. But
Meaning of this. Not that you take the
but if you take a very, very small open subset, then it's an isomorphism. But of these modules, these are just some sheaves over the spectrum of A, right? And if you shrink the spectrum of A sufficiently strongly, then it's an isomorphism. But on the boundary of this open subset, there might be some co-kernel. But it has smaller dimensional support. Okay? Just because well, we have some sort of vector space over field, and then you just need to know the dimension of this vector space, and that's it.
А вот самый конец. Мы поняли, что
So for this module, our claim is evident. It's manifestly free. And for this module, since it has smaller dimensional support, we know this generic freeness by induction assumption. And when we extend one free module with another free module, the extension is also free. So there we are. Right?
А почему берем F равный H?
Because we want to take the common, we know, well, there is U, whatever, U, like df prime in the spectrum of A, where T is free. We also have another dg in spectrum of A, where this is free. And there is this, their intersection, df prime g, where both are free. Okay. Welcome. Okay, so the corollary is the desired generic flatness. So we have an integral scheme S. It means that its structure sheaf has no zero divisors. And we have a projection from X to S of finite type.
If S is projected, can it be integral?
Pardon me?
If S is a projective variety, can it be integral?
Certainly, yes. Like, for example, the projective space is certainly integral.
Integral means it's a structure.
Integral means that the structure sheaf has no zero divisors.
The global sections on
All the varieties, I mean, all the irreducible varieties are necessarily integral. The bad things are either nilpotents in the structure sheaf or irreducible components where the product of this and product of that is zero. Okay, so I have a finite type morphism and a sheaf, coherent sheaf on X. Then there is an open, non-empty set U in S such that F restricted to the preimage of U is flat over U. Yeah, I mean, it's locally even free and a fortiori flat. So this corollary will be used throughout our whole study of Hilbert schemes. And now our next topic is some stratification. Well, I will formulate the theorem. It will be a long formulation. And the stratification in reality will be by Hilbert polynomials. But abstractly, it's some stratification by flatness strata. I mean, given a sheaf like this, well, we know that there is an open subset over which your sheaf is flat.
Looks like we proved that it is also a locally free sheaf.
Absolutely, yes. But we will need, well, if you remember some general results we did not really study regular or smooth schemes in this detail, but for them, local freeness and flatness are just, for coherent sheaves, are equivalent. Okay, so.
I understand that local freeness implies flatness.
And in fact, for coherent sheaves over regular schemes, it's just the converse is also true.
What's regular scheme?
Well, for varieties, it means smoothness, as we studied it. And for schemes, well, I think you also have heard some definition with regular sequences, Cauchy property, something like this. But never mind. Just over smooth varieties, for example, for coherent sheaves, freeness and local freeness and flatness are equivalent, but well, the direct image could be not coherent, right? It could be quasi-coherent, so it's not literally applicable here. What? Yes?
Вот у нас, когда мы перешли от многообразия к схемам, у нас же точек больше стало. И вообще
Yes.
топологическое пространство другое.
Absolutely.
Так же считается?
Absolutely, yes. Mm-hmm. The definition of dimension is literally the same.
Спасибо.
Absolutely. And the result is also the same. So if you take n-dimensional variety, like project space, for example, and view it as a scheme, then its dimension will be the same number. There are some non-closed points. We used to consider only closed points, but there are many more non-closed points, but they do not change your dimension. I mean, if you consider just spectrum of any field, then just by itself it has dimension 0. Even though the transcendence degree of this field may be high, yeah, just by itself has dimension 0. But well, if you consider, say, the generic point of a curve, then well, once again, by itself this will be dimension 0, but the whole thing will have dimension 1, and the dimension of the closure of this point will be one-dimensional. So this point by itself is 0-dimensional, but its closure is the whole curve and has dimension 1.
То есть размерность это абсолютная штука, не относительная.
Yeah, if you wish, yeah. Okay, so what was I saying? That given a coherent sheaf over some base, there is an open set of this base over which this coherent sheaf is flat. We take the maximal such open set, then we restrict our sheaf to the closed complement, and somehow we repeat this procedure, and we obtain some stratification of the base. And this next theorem, by the way, it's the first theorem in our study. So certainly this theorem is smaller than the existence of Hilbert schemes theorem, but still it's a theorem. So we're given a coherent sheaf over the projective space over a base scheme. And then the first claim is that the set of Hilbert polynomials of the fibers well, maybe I should say the Euler characteristic of f sub s of R, where S is a point in our scheme, this set of all possible Hilbert polynomials of fibers is finite. Okay, that's already something. So there are many points in the base, and in principle, you could imagine that the possible Hilbert polynomials of all the fibers could be very big, but it is not. And the proof is somehow almost clear, yeah, because you know that in the flat family, the Hilbert polynomials are constant. And then you know that there is some open set where it is flat, and then you take some smaller dimensional complement and just argue by Noetherian induction. So that's more or less clear. Okay, and now for any Hilbert polynomial, well, maybe let's just find it. Maybe it's, let us call it I. And for any polynomial in this set, there exists a locally closed subscheme SF in S, such that the following properties hold true. So first of all, the set of closed points SF is exactly the set of closed points such that the Hilbert polynomial of the corresponding fiber. Sorry. Is exactly f. Okay, this is very natural expectation. But the claim here is that this subset is the set of points of locally closed subscheme. So it's not some constructible subset or whatever, not some random subset. It's the set of closed points of a locally closed subscheme. So it has a nice structure. Okay, and in particular, the union of those guys is just the set of closed points of our base scheme. Now, the second claim is that.
But what was the claim about this set? It is finite set. Closed points is.
There are finitely many Hilbert polynomials of fibers, and for each of them, we take all the fibers with this given Hilbert polynomial, and then this set of points in the base scheme is the set of closed points of some locally closed subscheme. So, for example, it cannot look like this. You take the plane, like S, then you remove some line, but then you put back the origin. It's not a locally closed subscheme, it's a constructible subset, and it cannot happen this way. So you cannot have all the Hilbert polynomials equal to f over exactly this set. This is a bad set, not a locally closed subscheme. This does not happen. Okay, so this was the first property. The second property says that let's consider S prime just the disjoint union of those strata. Okay, so said theoretically, it is the same as our original scheme S, but scheme theoretically, nothing like this. So, for example, it could be like in similar example, it could be you take well GM times A1, the plane without a line, and the disjoint union line without a point, and then disjoint union just one point. Okay, so it will be a scheme not equidimensional with three connected components, yeah, and it is absolutely not the plane. Okay? So it's again something different, but we have a morphism to the original scheme S, just because all the subschemes, all the connected components, so to say, here are just locally closed subschemes in S. So there is such a morphism. Okay? And now this morphism is, so to say, the universal flattening morphism. Namely, first of all, the pullback of F, it is a coherent sheaf over projective space over S prime, is flat over S prime, and also, so to say, conversely, for any morphism phi from another scheme T to S, such that the pullback is flat over T phi factors through I. Okay.
So this phi star f should be
Yes.
over t for all f or for just one?
For this particular, we start with the coherent sheaf and we only work with it. It's fixed throughout the whole theorem. Only for this particular coherent sheaf.
So everything is dependent on f.
Oh yes, yes, certainly, yes. Everything depends on F.
Each strata.
Everything depends on F, certainly, yes. Otherwise, for example, we could take the structure sheaf of the partial space, and then there will be just a single strata, the whole scheme S. Very stupid thing. Or else we could take just the structure sheaf of one fiber, and there will be two strata, this particular point and everything else. And now,
I is not
Yes.
an embedding.
well, you may say that it's a locally closed embedding. Yeah, for example, the morphism into here is a locally closed embedding. Okay, so we say that I is totally ordered. Namely, we say that F is bigger than G if F of R is bigger than G of R for any big enough R. And it makes sense because there are finitely many polynomials, and in particular their degree is bounded by, say, 1 million. And then for polynomials of degree less than 1 million, they cannot swap their order infinitely many times. Yes, so when R is big enough, one of them is definitely bigger than everything else. And then the next one is bigger than everything else, and so on. So they are really totally ordered like this, just because they are finitely many. Pardon me?
Because the degree is bounded and they are
Yes, because the degree is bounded, yes. And then I claim that if we take one stratum, like SF, and take its closure, then it lies inside the union of G bigger than F of SG. So under specialization, your Hilbert polynomial can jump, cannot drop, can only jump. Okay, that's it. We succeeded in formulating this theorem, and now let's start proving it. And unfortunately, we will not be able to prove it today, but we will at least start. And we will definitely finish on Thursday. But then after we succeed with this theorem, all the preparations will be over, and we will start with proving, with constructing Hilbert schemes, or quad schemes. Okay, so we prove for an open and then affine cover of S, and then the strata for S, how to say, for UI will glue due to the universality property. Yeah, if we stratify for all the open subsets, then due to this universality, the strata will glue in all of them to form the global strata. So we can assume that S is affine. And then we start with n equals 0. So it will not be approved by induction. Not that then we'll move to n equals 1 and so on. N equals 0 will play some special role. So in this case, there is no project space. We're given a sheaf on the base itself, on S. Okay, and then we'll apply this to direct images of F or its twistings from project space. Okay, and then the Hilbert polynomials in question are very stupid ones. They're just constants. And there's F is now the sheaf on the base S.
Why?
Because P0 is just S. All the fibers are just 1 point fibers.
ENS now.
All the fibers of this space are just n-dimensional projected spaces. When n is 0, all the fibers are just points. So P0S is just S itself. And Hilbert polynomials are just constants. So there is no much variety in this case. Universal property number whatever 2. This. Yeah. Okay. Dimension over the field of residues at this point. And so let's fix this particular dimension, E, and then by Nakayama lemma, as Leonid ordered, as Schweid ordered, yeah. There is an open neighborhood V of our point S. Yeah, we always study Hilbert polynomials, but in case the ambient projected space is 0-dimensional, all the possible Hilbert polynomials are just numbers. There are no twistings, nothing at all, so they're just constant numbers, degree 0 polynomials. And we fix such a positive integer E, and then we had this argument like half a year ago that around this point we have a locally free presentation like this. So you just by Nakayama lemma, since in the fiber you have exactly E generators, you need just as many E generators over the local ring, and then actually I don't have to invert everything away from this maximal ideal, but only finitely many. Well, just you have to invert some particular denominator, so it's global in some neighborhood. Okay, there is such a presentation, and let IE be the ideal generated by all the matrix elements of psi. Here, yeah, it's M by E matrix, and VE inside V, it's a closed subvariety, the zero set Z of IE. So where all those matrix elements vanish. So then for any morphism gamma from T to V, from some test scheme T to V, we can just pull back this short exact sequence, and we obtain OT to the power M goes to OT to the power E, goes to the pullback of F. And we conclude that the pullback of F is locally free of rank equal to E, if and only if the pullback of psi is 0. Yeah, because already here we have locally free sheaf of rank E. So in order for the quotient to be such, you don't want any kernel. Okay.
Who is VL?
Pardon me?
Who is VL?
VE here, yeah? Well, E is this number, so we want our sheaf to be locally free of rank E. Well, this is the same E.
We find some.
I can erase this E if it doesn't help you.
Some set.
I wanted to write down some locally closed subscheme. Well, I'm proving the theorem for n equals 0. So I'm finding this locally closed stratum for the Hilbert polynomial E. Okay? And here is open, here is closed, and their intersection will be locally closed. This is open subset, this is closed inside open.
IL is an ideal sheaf of VL.
So it's E, it's not L, it's E.
Yes,
It's also E, but
IE is an ideal sheaf of
yes.
VE.
Right, absolutely, yes. Yes. Fine. Well, this is equivalent to the fact that gamma factors through the embedding, the closed embedding, like this. And so we proved parts 1 and 2. Okay. Yes. Pardon me?
Причем тут VE? Ну, последняя относительность откуда берется?
This one?
Да.
Well, so we need this property that pullback of psi is 0, but psi is a matrix, right? And this is the ideal generated by all the matrix elements of this matrix. So the pullback of psi is 0 is equivalent to the fact that we are lying in the 0 set of this ideal. So our gamma factors through this closed embedding. Okay. Okay. So we proved this and that, and only need to prove this closure relation, which is also clear. So it follows from the fact that the rank of psi is semi-continuous how to say, from below is lower semi-continuous, and hence E. Why the rank is lower semi-continuous? I think we also proved this some long time ago, but just because the matrices of rank E is an algebraic, the closed algebraic subvariety given by equations that all the minors of rank E plus 1 vanish. So the rank of psi is lower semi-continuous, hence E is upper semi-continuous. Okay. And so we proved this theorem, which I just erased, for so just for sheaves on the base S, and now we move to sheaves on the relative projective space. So now n is bigger than 0, and we will construct our stratification, flattening stratification, by intersecting the n equals 0 strata for various sheaves push forward of F twisted by R, like this. Okay, so the logic will be as follows. We proved for sheaves on the base, and now the sheaves on the base we will use will be such push forwards, but we will only need finitely many, as you will see. Okay, so so we start with an irreducible component of S. And let U be the dense open subset, the complement to all the other irreducible components. So I'm setting the stage for Noetherian induction. Okay, and well, we equip U with a structure of integral locally closed subscheme of S. I mean, S could have some nilpotence to begin with, but I want this U to be integral. So it will be not just open, but locally closed. I mean, let S be irreducible to begin with, but with nilpotence. Then I want to kill all the nilpotence, and I will get this closed subscheme of S just by killing all the nilpotence. Okay. And by the generic flatness corollary, there is open subset V in U such that F restricted to this open subset is flat over V. Now we can replace S by the complement of this open subset, and again pass to the reduced structure, and by the Noetherian induction, there are locally closed reduced subschemes Vi such that the union of their closed points is just the whole of S, and F restricted to the corresponding locally closed subspaces are flat over Vi. Okay, and since in the flat families the Hilbert polynomials do not vary, we conclude that there are only finitely many Hilbert polynomials well, Fi's of the fibers and thus the first part of the theorem is proved, and we have to prove this universality property. The fibers, so P S of M is the Euler characteristic of the fiber okay. And well, let's we proved this, and let's call this statement, this finiteness statement, let's call it A. I will now also formulate two more statements, B and C, and then we'll have to stop, and then next time we'll start from this point. So we'll assume those three statements, A, B, C, and we'll prove the theorem just from these statements B and C. So from Grothendieck semi-continuity theory. Remember, we spent a week or more proving that for any sheaf on projective scheme over the base, its direct image can be computed by some, or at least locally, by some finite free complex, K bullet. And that's what we use. And from this we derived many nice corollaries that I will use right now. And in fact, this Grothendieck theorem was proved by Grothendieck exactly for this. So while he studied Hilbert's scheme and proved its existence, he discovered this method. Okay, so that's exactly what was it designed for. So from this, it follows that there exists some big enough positive integer such that all the higher direct images vanish if we twist by big enough twist, and this computes with the base change. So Arth cohomology of all the fibers are also zero under the same assumptions for all the fibers. Okay, and this is property B.
This will prove next time.
No, this is already proved. We proved this a month or so ago. I just recall the yes. So we already know this flattening statement, and from this flatness, we deduced this Grothendieck theorem worked for flat sheaves over project spaces. So since we know this, we know that. Next time we will use this in order to deduce the universality of our stratification. So we already produced stratification by Hilbert polynomials, and now we want to prove that it's the universal flattening stratification. So now I'm formulating the last property C, and then we adjourn. So last time we proved lemma 1, which was base change up to big enough twist. Yeah, and from this lemma, for any stratum, there is, and for well, again, we can choose still bigger twist, R, I, such that for any m bigger than Ri, the push forward of f of m restricted to Vi will be isomorphic to the push forward of f restricted to Vi. Okay, so pi I is the base change from Pn Vi to Vi. Okay. Now the higher cohomology of fibers vanish by the property B after this twisting from the semi-continuity for flat morphisms F, well, flat, I mean not morphs but sheaves, FVI over BI. We conclude that for any point in the stratum VI, there is a base change isomorphism PI push forward FVI of M. The fiber over S is isomorphic to the global sections of the corresponding fiber. Okay, is that the base change isomorphism we deduced some time ago, and that's true for any M high enough, bigger than this particular number, and taking the common value of all those guys for finitely many strata, and composing those isomorphism, this and that, we obtain the desired property C. Okay, next time we will start from A, B, C. So for any n, there exists n bigger than n1, such that the fiber of the push forward at point S is isomorphic to the global sections of the corresponding fiber with coefficients in the twisted sheaf. Okay, and now this is for any m bigger than n, and for any fiber. Okay, that's it. And next time I will recall those properties A, B, and C, and from them we will deduce our theorem. And then we will be in the position to construct Hilbert schemes. Okay? Thanks. Bye-bye.
What did you mean when you compress from S to S minus?
Means I take the reduced scheme with the same support, so it is a closed subscheme given by some ideal. And this ideal is just the radical. So I kill all the nilpotents.
Say S is the spec of E divided by X.
Yes, for example, if S is the spectrum of dual numbers, then S reduced is the spectrum of K. I kill the nilpotents. It has the same topological space, but the structure sheaf is some quotient sheaf, namely the quotient modulo radical, modulo the radical.
This is in general a subscheme of S.
Yes, it's a closed subscheme of S. Mhm. The maximal reduced subscheme.
Why it is closed?
Because it is defined by some ideal,
With a nil radical.
the nil radical. Yes.
How does this implication, the last application work? So here we had some VIs.
Yes.
Here's no VIs.
But just you have such isomorphisms for the points in strata. There are finitely many strata, so you can take the common twist big enough, and there you are.
For each point?
For each point, yeah, you have the composition of those isomorphisms is this isomorphism. Yeah, you can forget everything, yeah. And next time I will recall those properties A, B, and C, and we will deduce our theorem from A, B, and C. Thank you.